Have you ever looked up at the night sky and felt a sense of wonder? The sheer scale of it all is simply breathtaking. We see countless stars, distant galaxies, and vast clouds of cosmic dust. For centuries, we believed this was everything, our universe, the one and only. But what if that is not the whole story? What if our universe is just one of many? Imagine for a moment that our entire cosmos, everything we can see, measure, and comprehend, is merely a single bubble floating in a much larger, unseen ocean of other universes. This is not science fiction. It is a mind-bending idea that comes from the cutting edge of modern physics. It poses the ultimate cosmic question. Are we alone in the cosmic sense, or are there other universes out there, perhaps just beyond our reach? And if they exist, could they collide? For nearly a century, our story of the cosmos has started with the Big Bang. It is a powerful and well-supported theory that tells us our universe began from an incredibly hot, dense point about 13.8 billion years ago. From that singular moment, it has been expanding and cooling ever since, forming the galaxies, stars, and planets we see today. But what if the Big Bang was not the beginning of everything? Some physicists now propose that the Big Bang was not a unique, one-off event, but the result of something even more fundamental happening in a higher dimensional space. According to this theory, the Big Bang could have been triggered by the collision of two such branes. Picture two massive, universe-sized membranes drifting through higher dimensional space, building up energy until they collide in a cataclysmic impact. To understand how universes could possibly collide, we first need to look at one of the most ambitious ideas in physics: string theory. For decades, scientists have been on a quest for a theory of everything that could explain all the fundamental forces of nature. String theory proposes something radical, that if you could zoom in on fundamental particles, you would find they are all made of minuscule, one-dimensional, vibrating loops of energy. These are the strings in string theory. For string theory to work, it needs more dimensions than the 3 we're familiar with. Most versions predict 10 or 11 dimensions. These extra dimensions are thought to be curled up so tightly that they're invisible to us in everyday life. String theory also allows for vast, extended objects called branes, short for membranes. Our familiar 3-dimensional world might just be one of these branes, floating in a much larger, higher dimensional space. Let's try to paint a clearer picture. Imagine our universe is a gigantic flat pond. All the fish, the plants, and the ripples on the surface represent the galaxies, stars, and energy within our cosmos. We are like the fish, living our lives completely within the confines of our 3-dimensional pond, completely unaware of the vast space that might exist just beyond the surface. We are brane worlders, through and through. This model, where we live on a brane embedded in a higher dimensional bulk, is known as the Randall-Sundrum model, proposed in 1999. It elegantly addresses why gravity seems so feeble compared to other forces. In this larger arena, our brane is not alone. There could be other branes, other universes existing parallel to our own, just a fraction of a millimeter away in a higher dimension, yet completely inaccessible to us. Picture not just one membrane, but an entire collection of them, all coexisting within the higher dimensional bulk. This is the heart of the multiverse concept in Brane Cosmology, multiple 3-dimensional universes floating like pages in a cosmic book. This cosmic ocean is not static. The branes can move, warp, and ripple. They are dynamic objects, influenced by their own internal energy and the gravitational pull of their neighbors across the dimensional divide. This framework forces us to reconsider what universe even means. Is it just our brane, or is the true universe the entire bulk with all the branes it contains? For our purposes, we can think of each brane as a self-contained universe with its own physical laws and history. This perspective demotes our entire cosmos, with its billions of galaxies, from being the entirety of existence to being just one island in a potentially infinite archipelago of worlds, a single bubble in a vast cosmic foam. If there are other universe branes out there, what might they be like? The possibilities are truly mind-bending. Some might be almost identical to ours, while others could be unrecognizably alien with different fundamental particles and forces. This concept offers a solution to the fine-tuning problem, why our universe seems perfectly tuned for life. If there are countless branes with randomly determined physical laws, it's not surprising that at least one would have the right combination for life to emerge. This multiverse of possibilities opens new avenues for scientific thought. Perhaps the mysteries of our universe, like dark matter or dark energy, could be explained by interactions with other branes. Could dark matter be evidence of matter on a parallel brane? The Brane multiverse concept is not just a philosophical curiosity. It provides a new toolkit for physicists trying to solve the most profound puzzles about our own reality. If these other universes exist so close, yet so far, is there any way we could ever know for sure? While we cannot travel to another brane, theory suggests they might not be completely silent. Gravity is our potential messenger between worlds. The gravitational pull from a massive object on a nearby brane could, in principle, be felt on our own. Its gravity would leak through the bulk and affect the motion of stars and galaxies in our universe. Another place to look is in the sky's oldest light, the cosmic microwave background. This faint afterglow of the Big Bang carries an imprint of the universe's earliest moments. If another brane had been close to ours in the distant past, it might have left a subtle gravitational mark. The Large Hadron Collider offers another way to search for evidence. By smashing particles together at enormous energies, physicists hope to recreate early universe conditions. These collisions could be powerful enough to knock a particle off our brane and send it into the bulk. The idea that our universe was born from a collision is part of a detailed cosmological model. Around 2001, physicists proposed the ekpyrotic model, from the Greek word meaning coming out of fire, suggesting our universe was created from a fiery clash between two parallel branes. In this scenario, the story begins not with a bang, but with a long, slow approach. Two cold, empty branes drift towards each other for trillions of years, building up immense gravitational energy. As the branes make contact, the colossal energy stored in their approach is released in a flash. This energy transforms into a hot, dense plasma of fundamental particles, the fire in the ekpyrotic model. This searingly hot fireball is essentially identical to the state predicted by the Big Bang model. From this point onwards, the evolution proceeds familiarly. The plasma expands and cools, particles form atoms, and eventually stars and galaxies begin to form. The collision provides the starting pistol for the cosmic race we know. What exactly happens during one of these universe-shattering collisions? As the two branes draw closer, the energy in the interbrane space builds up immensely. The collision doesn't happen all at once. It begins at one point and ripples outwards. The collision is not a physical smash, but a conversion of energy into the raw material of a new universe. The phenomenal energy released creates a hot, dense plasma of quarks, gluons, electrons, and photons that filled the very early universe. One elegant aspect of this model is how it accounts for the tiny fluctuations we see in the CMB. These are the seeds of all cosmic structure. Without them, the universe would be smooth and featureless. In the ekpyrotic model, quantum fluctuations on the brane surfaces cause slight timing variations in the collision. This gives us a physical mechanism for creating the universe we see, a process driven by string theory and gravity in higher dimensions. It elevates the idea of colliding universes from science fiction into a credible scientific hypothesis. The ekpyrotic model doesn't just describe a single collision, it opens the door to an eternal cycle. After the branes collide and create our universe, they don't stick together. Instead, they pass through each other and begin to move apart again. For billions of years, stars will form and die, galaxies will evolve, and life may flourish, all while the two branes are drifting away from each other in the bulk. But this expansion cannot last forever. After an immense stretch of time, our universe will become cold, dark, and virtually empty. The stars will have burned out, and black holes will have evaporated. This is the ice phase, but gravitational attraction between the branes slowly pulls them back together. They start another long journey towards each other, setting the stage for the next collision. After trillions more years, they collide again, creating a new universe with fresh matter and energy. The cycle of fire and ice begins anew. Our Big Bang was not the first, and it will not be the last. It is simply one beat in an eternal cosmic rhythm of collision, expansion, cooling, and contraction. This vision suggests that time has no beginning and no end. The cosmos is eternal, constantly reinventing itself. It means our universe is not a singular event in an eternity of nothingness, but part of an endless, self-perpetuating cosmic engine, a timeless dance of universes being born from the ashes of their predecessors. What would such a cataclysmic event look like from inside our universe? If another Brane were on a collision course with our own, we would likely have no warning at all. It would be the ultimate stealth catastrophe, approaching silently through a dimension we cannot perceive. The first signs would appear as strange gravitational effects, anomalies that would send cosmologists scrambling for answers. As the other Brane drew close, its gravitational influence would begin to dominate our cosmos. The final moments would be a spectacle of cosmic horror. The sky would no longer be dark but would glow with intense light, as if a new sun were being born in every direction at once. The very atoms that make up our bodies would be torn apart by unimaginable forces. From our perspective, it would feel as if the universe itself were collapsing and igniting simultaneously. The collision would happen everywhere at once, as the entirety of our three-dimensional reality met the other. For any observer, the experience would be mercifully brief. The collision would represent a total reset button for our universe. It is an event of such fundamental violence that no structure, no information, and no history from our current cosmos could possibly survive it. Every galaxy, star, and particle would be dissolved into homogeneous, searingly hot plasma. But this ultimate end is also an ultimate beginning. The phenomenal energy released would instantly create conditions for a new universe to be born. This is the great paradox. It is both supreme destruction and supreme creation. What would this new universe be like? It could be a near-perfect replica of our own, or wildly different with stronger gravity, different particles, or even a different number of spatial dimensions. The slate is wiped so clean that almost any outcome is possible. This concept forces us to confront the mortality of our entire reality. Our 13.8 billion-year-old cosmos is just one chapter in a book with an infinite number of pages. The death of our world would be the price of birth for the next. It's crucial to understand how this vision differs from the classic Big Bang singularity. In the standard model, the universe begins from a point where physics breaks down completely. The Brane collision scenario avoids this singularity. It's a violent event between well-defined objects in pre-existing space. This provides a more complete picture of our origins. Instead of asking what came before the Big Bang, a meaningless question in the standard model, we can ask what the Branes were doing before they collided. Our universe emerged from a physical process governed by gravity and string theory. This idea also changes our perspective on the future. The cyclic Brane model offers an escape from eternal decay. It promises not just an end, but a renewal, a fiery rebirth that will kickstart a new era of cosmic evolution. It is a far more dynamic and optimistic vision of reality's ultimate fate, where the end of one story is always the beginning of another. This framework suggests our entire cosmic existence is just one cycle in an eternal dance of creation and destruction. After exploring these mind-bending theories, we must return to evidence. Scientists have become cosmic crime scene investigators, sifting through ancient evidence of our universe's birth for any clues. They're looking for fingerprints that a dramatic event like a Brane collision might have left behind. Their primary exhibit is the oldest light in the universe, the cosmic microwave background. This faint radiation is a snapshot of our universe when it was just 380,000 years old, and it holds vital clues about its origin. The standard inflationary model and the ekpyrotic collision model make different predictions about gravitational waves. Inflation predicts strong primordial gravitational waves, while an ekpyrotic collision would produce a far weaker signal, perhaps undetectable. Telescopes like the BICEP array at the South Pole are designed specifically for this task. They meticulously scan the CMB, looking for B-mode polarization patterns, the telltale signature of ancient spacetime ripples. The cosmic jury is still out. Beyond gravitational waves, scientists hunt for more direct scars that a Brane collision might have left. If our universe was born from such an event, it may not have been perfectly uniform. A collision could have created large-scale wrinkles in the fabric of spacetime. In 2004, astronomers discovered the CMB cold spot, a vast region that is anomalously cold and so large that its existence is highly unlikely to be random. Some physicists speculate this could be the very bruise we're looking for. Of course, this is highly speculative. There are conventional explanations. It could be caused by a massive supervoid with fewer galaxies than average. The debate rages on, and scientists continue to study this patch of sky. The search for these large-scale anomalies is crucial for testing Brane cosmology. We are searching for the lingering echoes of that ancient cataclysm. Finding a definitive cosmic bruise would provide compelling evidence that our universe's history is far more dramatic than we imagined. While astronomers look to the heavens, particle physicists look to the infinitesimally small. At the Large Hadron Collider, scientists conduct experiments that could provide different proof for Brane cosmology. The theory is built on string theory's prediction of extra-spatial dimensions. The idea is to smash protons together at nearly the speed of light, creating tiny fireballs of immense energy that replicate early universe conditions. If extra dimensions are large enough, these collisions could create microscopic black holes or knock particles off our brain. We couldn't see an escaping graviton directly, but we could infer its existence by what it left behind, a deficit. Our detectors are designed to capture every particle. If energy and momentum were missing, it would violate conservation laws, the smoking gun evidence. So far, the LHC has not found definitive evidence of extra dimensions or missing energy, but the search continues. Every new run brings the possibility of a breakthrough that could turn the multiverse from theory into tangible science. We have journeyed to the absolute frontiers of modern physics, from the infinitesimally small vibrations of strings to the colossal scale of colliding universes. We began with a simple question: could our universe be one of many, and could these universes collide? The theories we've explored suggest the answer could be yes. This radical idea reframes our entire existence, demoting our vast cosmos to just a single membrane floating in higher dimensional space, both humbling and exhilarating. We've seen how this framework offers potential solutions to deep puzzles: the weakness of gravity, the fine-tuning of our universe for life, and even the Big Bang itself, recast not as a beginning from unknowable singularity, but as the consequence of two parent universes meeting. This is not just philosophical speculation, but active scientific research. We followed cosmic crime scene investigators searching for clues in ancient light and smashing particles to probe for extra dimensions. Through it all, we're left with more questions than answers. The ideas of Brane cosmology represent humanity's most audacious attempt to understand our place in the cosmos. But it's important to remember this is science on the absolute edge. String theory remains a mathematical framework yet to be experimentally proven. The concept of a multiverse presents a fundamental challenge to the scientific method. How can we test the existence of other universes that may be forever beyond our reach? Scientists are clever, devising indirect tests, but we must distinguish between theoretical and proven. This doesn't diminish the importance of these ideas. Theoretical physics plays a vital role in guiding our search and expanding our horizons. These theories give us new questions to ask and inspire the development of new technologies and experiments. We're left to reflect on the mysteries that remain. The nature of dark matter and dark energy, the universe's accelerating expansion, and what happened before the Big Bang are all profound unknowns. Brane cosmology offers a tantalizing, unified narrative that could potentially address all of them. What does the future hold for our quest to understand Brane cosmology? The voyage of discovery is far from over. The next generation of cosmological surveys and space telescopes will map the universe with unprecedented precision. New CMB experiments will continue hunting for primordial gravitational waves, while the high-luminosity Large Hadron Collider will increase collision rates by a factor of 10, searching for rare phenomena with far greater sensitivity. This two-pronged attack, peering ever further into the cosmos and ever deeper into matter, is our best hope for finding answers. The intersection of cosmology and particle physics is where the greatest discoveries of the 21st century are likely to be made. The quest to understand if universes can collide speaks to our deepest human desire to comprehend our origins and destiny. Whether our universe is singular or one of infinite branes in a cosmic ocean, the pursuit of that knowledge defines our species. We are explorers on an ongoing voyage, sailing the vast seas of the cosmos with our instruments of science and boundless curiosity. We stand at a precipice, staring into a universe of new and profound questions about the nature of reality itself. The final answer may lie just over the next horizon, waiting for a new discovery to finally reveal the true and likely astonishing nature of our cosmic home. The story of our universe is written in both the stars and the atoms, and we must learn to read both languages to fully comprehend it. Whether our universe began with a singular bang, or with the colossal impact of two membranes in a higher dimension, whether its fate is a slow fade or another spectacular collision, one thing is certain: we live in a cosmos far stranger, more beautiful, and more magnificent than we ever dared imagine, and that journey of discovery has only just begun.